Okay, a couple things. I posted the quiz today, and it's under quizzes and under assignments. But if you go under quizzes, probably the most straightforward way to find it. And it's proctored via Proctoria. Now, that's what this school uses. Now, this is the first time I'm using Proctoria as well. Basically, I've given you.
Come on, you piece of piss. Oh.
Are we okay? I've given you 30 minutes to do the quiz, which I think is way more than enough time. So you should feel comfortable doing it. You have till midnight Saturday. Actually, you have till 11:59 Saturday to get it in. Okay. Also, when you're doing the worksheets, if you find an error, or you think you found an error anyway, please let me know, because there was already one that I made a mistake on a Sig Fig. So make sure you let me know, and I'll immediately correct it, and then issue an update, as well as let you know what the correction is. So you can either download it again, or you can just fix your copy. Either way. Okay, any other questions, you guys? Okay, why don't we go ahead and start? Okay, whenever we do problems in this class, we're going to be using a process called dimensional analysis. Now, that's a fancy description of what we're doing. Really, what we're doing is we're taking, like I gave the example last time, said we have 5 quarters. How many pennies is that? Okay, and I also gave you a 4-step procedure to use, which is similar to this one here. I like to use it more than this one. I think this one's got some clarity issues. But anyway, so this is the process that I've been using for at least 55 years. And it's a pretty basic process. Basically, whenever we have a problem in this class, because it's a chemistry class, you have to ask your question, is there a chemical reaction going on? The answer is no, then you can skip step 1. Now we're going to be doing problems where there is a chemical reaction later on in the course. But right now, the problems we're going to do for Unit 1 are not going to have any chemical reactions going on. So basically, step 1 is you can ignore that. Secondly, what's given? What are you trying to calculate? And then the conversion setup. Okay, so here we have this problem here. I said, you have 5 quarters. How many pennies are in 5 quarters? Excuse me. Okay. So what's given? Whenever you trying to figure out what's given, is you look for the number. In this case, it's the number 5. Okay, and what is the unit associated with that? And that is quarters. So given is starting with 5 quarters. That goes on the left. What are you trying to calculate? Well, then you look for a unit with no number associated with it. In this case, pennies, but there's no number associated with it. That's what we're trying to calculate. That's number 3. Then we need to set up the problem. To set the problem up, we're going to put the given on the left, what we're trying to calculate on the right. So here's the given. Let's do this in another color. Let's do it. I'm going to put the given on the left, and what we're trying to calculate on the right. going from given, what we're trying to calculate is going to be the conversion factors, which I call the setup. Conversion factors are fractions, and the fractions are known equalities. For example, now we said conversion factors or fractions. Conversion factors are always fractions. They start with an equality. For example, how many minutes are in an hour? Well, there's 60. So there's 60 equals 1 hour. That way we can form a fraction with 60 minutes over an hour or 1 hour over 60 minutes. 7 days a week, 7 over a week over 7 days. Now, within the problem, either the problem will tell you some kind of quantity relationship, or you have to look it up on the net. Now, on the test, now your quiz is not going to involve any dimensional analysis problems because we didn't cover that till today. But on the test next week, you are going to have a number of problems. Now, either if it wasn't a test, you would be free to look that up on the net. Now, because it's a test and you have a lockdown browser, I'm going to give you all the conversion factors you might need and then some. I'm going to give you a big list. And the list is going to have a whole bunch of stuff on it. And you're going to have to go through the list and figure out what conversion factor makes sense for the problem. Okay, so let's go back up to this problem here. Now, this problem involves pennies and quarters. So you're going to be looking for conversion factors that have quarters and pennies in them. That could be one conversion factor or multiple conversion factors. You're to grab any conversion factor that has the given or calculated in it. Now, in the case of this problem here with how many pennies are in 5 quarters, that's a relationship of $25 pennies is equal to 1 quarter, or 25 pennies per 1 quarter, or 1 quarter for 25 pennies. Now, it could be that you may have to use multiple conversion factors to get there. In this case, there was one. Sometimes you may have one conversion factor that's quarters in, another conversion factor that's pennies in it, and then you have to relate those together. And I'll be giving you some examples on how to do that in a minute here. Okay, so then the next step is, which of these conversion factors are you going to use? The 25 pennies over 1 quarter or 1 quarter over 25 pennies? In this case, we want the quarters to cancel. So that means we're going to use the 25 pennies over 1 quarter. That way the quarters cancel, giving us pennies. Okay. Basically, what this means is we always want the given to be canceled by the conversion factor. Now, when I say factor, factors, plural. It could be more than one. Usually it is more than one. Okay, and then we just grind it up. 5 times 25 is 125 pennies. Okay. And by the way, how many sig figs is 5 quarters?
One.
1, yeah. How many sig figs is 125?
3.
3. So how would we convert that to 1 sig fig? 125. Because our answer has to be of the lowest precision among the units we're working with here. How will we convert a 125 to 1 sig fig? Okay, let me go over this process. Whenever we're converting from one number of sig figs to another, we go to the second, or we go to the place afterwards. So if we're converting to 1 sig fig, we go to the second sig fig of the number, which in this case is a 2. That means we drop it because it's 4 or less, meaning that would be converted to 100 pennies. We were converting that to 1 sig fig. Okay. All right, let's now. Now, these notes are from Dr. Dowell, and he uses, instead of calculated, he uses wanted unit. Given unit, calculated unit. Same idea. And we have conversion factors to go from starting to wanting, going from given to calculated. Same idea. Let's look at another problem here. Okay, 19 years old, how many seconds have you lived? Okay, well, what's given in this case? Okay, first of all, is there a chemical reaction? No, don't have to worry about that. So number 2, what's given? What's given is 19 years. And what are we trying to calculate? Seconds. Okay, so the deal is, do you know of a conversion factor to go from years to seconds? I personally don't, but I do know some intermediate conversion factors that have years in it and that have seconds in it. Okay, there are 60 seconds per minute. There are 60 minutes per hour. There are 24 hours per day. We're in 65 days a year. So we have year and we have seconds. So we've identified two conversion factors to get us from years to seconds. But it isn't one conversion factor. So somehow we have to link these two together. So the way to do that is to think in terms of what is with 365 days a year? Is there another conversion factor that has days or year in it? Well, this has got day in it. But it's got hours in it, not seconds. Is there another way that we can go a conversion factor that has hours in it? Yes, over here. This has minutes in it, not seconds. Is there something that has minutes in it? Yes, this guy here. Okay. So via those conversion factors, we can make a link that gets us from years to seconds. Okay, so working from left to right, we're going to use conversion factor that has year in it. We've now converted 19 years to days. Now we're going to take the days and convert that to hours. Now we're going to take the hours, convert that to minutes. And then we're going to take the minutes and convert those to seconds. I want you to notice, we started with years and everything canceled unit-wise except seconds. And what are we trying to calculate? Seconds. So what we're going to do now is then, this would be the setup. Now the other way to do this is something, the layout would be something like this. Instead of parentheses, we're going to use solid lines. As opposed to parentheses. Some people use parentheses, some people use, they call this train tracks. I think the train tracks is a little more less cluttery than parentheses. They're both the same thing. So basically I substituted a solid line for these front and back parentheses. That's the only thing. Okay, so to work this problem, we're going to go 19 times 365 times 24 times 60 times 60. Okay. All right. And this is what my calculator gives me. Now, 2 sig figs, these are all by definition. So those don't count when we're calculating sig figs because those are all perfectly precise. So our answer has to have 2 sig figs. Okay, that means we're going to go to the third place, which is a 9 that kicks that 59, 1 up, that makes that 60. Now that's an awkward number, so let's convert that to scientific notation. Notice I put the 6 by itself because we need 2 sig figs. And there are 1, 2, 3, 4, 5, 6, 7, 8. So that 19-year-old person has lived 6 times 10 to the 8th seconds. So this is a typical multi-step problem. I want to go over this again. This problem has got a lot of important parts to it. What we've done is starting with step number 2, what's the given? 19 years. We're trying to calculate seconds. Okay, so we need some conversion factors, or one conversion factor, hopefully, that goes from years to seconds, and there isn't one. So now we have to relate, think of them as secondary conversion factors, together to bridge the gap from years to seconds. Then we're going to string those together so that the units keep canceling, the days, years, hours, minutes, and seconds. So we end up with leaving seconds by itself, because that's what we're trying to calculate. Once we get the setup done, then we just grind out the numbers and make sure our significant figures are consistent. That problem was worth 10 points. 9 points would be given to the setup, 1 point for the answer. By the way, 365 days in 1 year, not counting a leap year. If we counted in the leap years, we'd get a slightly different number. Okay, our notes call that a conversion pathway. What we're doing is we're just linking conversion factors together to get us from the given to the calculated. We have to make sure we put the conversion factors in such a way that the units cancel appropriately, so we are left with what we're trying to calculate. Okay. Let's look at this guy. You save a quarter per day. How many dollars would you have after 4 years? Well, okay. Excuse me. What's given? 4 years given. And what are we trying to calculate? Dollars. Okay. So what we're going to do is then start with the given, 4 years. We're going to make this exactly 4 years. Okay. And what are the conversion factors? Well, one conversion factor is this here, 1/4. Per day. So when we want to go from years to money. Okay, so we've got Do we have any conversion factors with a year in it? Well, what do we know about years? Well, how many days are in a year? Okay, there are. The 365 days in a year. What else here? Any conversion factors that involve a dollar? Well, we know that there are 4 quarters in a dollar. Okay, is that going to do it? Let's see, we got years. We have dollars. We have days here, quarters here, quarters here. So using these 3 conversion factors, we can link those all together to go from years to dollars. Okay, so first step is to cancel out years. Well, we have years right here. Okay, that gives us days. Okay, we can convert quarters to days here. And now we're going to go from quarters to dollars. So we've canceled out everything except dollars. And what are we trying to calculate? Dollars. Now we just have to write that out and keep our significant figures consistent. So we have 4 times 5. Okay, so that gives us $365. We started off with 3 sig figs. We end with 3 sig figs. Yes. Now, this process is kind of, you have to kind of get used to it. And we start searching for conversion factors that relate to one another. Then you're going to end up stringing them together. This process is used in physics, it's used in engineering, it's used in chemistry, it's used in computational biology, it's used in geology, it's used everywhere where quantitation is needed. It's a very common process. Okay, you guys feeling okay? Now, this would be typically what I give you on a test. I give you a bunch of conversion factors like this. And whatever you think you know about conversions, you are to use the ones I give you because that's what the key to the test or quiz is going to be based upon, are the ones I give you. Okay. Let's come up with another problem here. Let's see. Oh, I have an idea. This is a problem I ran across a while ago. It's very interesting. And it had to do with dimensional analysis. And this is a real life problem. And I need to okay, this really happened. 1983 in Canada, and again, Canada uses the metric system, the SI metric system. This plane crashed, and the reason why it crashed is it ran out of fuel. The guidance for the ground crew was to fill the plane with 22,300 kilos of fuel. They put in 22,300 pounds of fuel instead. Why was that a problem? Well, how does pounds and kilos relate? Well,
Kilograms are larger.
there's a difference in size, huh? If we were to bop over to here, and yes, you're right, and look up pound to kilogram, it appears like a kilogram is less than a pound, or a pound is more than a kilogram. Okay. So if we have, let's just say a kilogram is 0.45 pounds. So we're going to convert 22,300 pounds to kilograms. What will we end up filling that plane with? Well, so instead of 23,300 pounds, we really put in there the equivalent of 10,035. So instead of needing the 22,300 kilograms, we only put in there 10,000. Hence the plane ran out of fuel, and the pilot was able to land the plane safely, and no one was killed, but it was a simple error of systems. The SI metric system versus the imperial system, and they do not mix. There was an error made a while ago when we first started landing on Mars. We had a drastic error, and it was the same deal. There was an engineer that used imperial measurements instead of metric measurements, and we had some massive failures as well. So now this happened to be an easy problem. It was a one-stepper because we had kilogram and pound in the conversion factor. But these kind of errors actually happen a lot. And that's why I wish the world would, I should say, I wish the United States would switch over to the SI metric system as soon as possible, because we'd eliminate stuff like this. Okay, let's see now. There is another conversion factor, excuse me, that's used a lot in chemistry and geology and physics as well, particularly in chemistry and geology, and that's density. And density is a relationship between mass and volume. And it's unique because the density is unique per compound at a given temperature. And let me give you an example of that. During the gold rush, many prospectors would find something that's yellow and shiny, and they would mine it, and they would bring it in, and they would expect to be getting a lot of money for it. Well, there are two things when you mine up in the gold-bearing area of the foothills that is gold and shiny. That is iron pyrite and gold. And iron pyrite is not gold. Iron pyrite is worth almost nothing. Gold is worth lots of money. So how do they tell the difference between iron pyrite and gold? They did it via density. Now, if you look up gold, iron pyrite. Has anyone heard of iron pyrite?
Is that fool's gold?
Yep, fool's gold. So you would take your chunk of shiny metal. There's some other ways to tell the difference between fool's gold and gold besides density. There's some crystallization patterns that are different, but density is definitely one way. If you were to weigh your whatever, okay, so this is the steps you use. First of all, you need to determine those are all commonly seen measurements for density. Grams per milliliter, grams per cubic centimeter, or grams per cc. Those are all the same thing. cc stands for cubic centimeters. cm cubed is cubic centimeters, and ml is milliliter. Chemists usually use grams per milliliter. Physicists go grams per cubic centimeter, and medical people go grams per cc. It's just, they're all the same thing though. So the numbers you see are, notice here we have cubic centimeters, but same thing as milliliters of water. Okay, so you need two parts to determine density. You need a mass and you need a volume. Okay, the mass is easy. You put it on a scale, measure the grams. Okay, so we bring in, this would be gold. Fool's gold. Weigh them both. The next thing you need to determine is volume. Now, volume is really tricky because gold never comes in a nice cube. It comes in a very irregular shape. Same with fool's gold. So how would you suggest we find volume? By the way, the mass of the density of fool's gold is 5.0 grams per cubic centimeter. So how would we find the volume? Has anyone ever heard of Archimedes? Okay, Archimedes is a famous Greek guy, and he noticed something when he was getting into a bathtub of water. The water would go up. All of you experience this. If you've ever taken a bath, you sit in the bathtub, and what happens to the water? It goes up. Why does it go up?
It gets full.
Yeah, your body pushes the water out of the way. And where does it go? It can only go one place because it's in a tub, so it has to go up. So it's called displacement. So how much water did you displace when you sat in the tub? Well, if you were totally submerged, it would be the volume of your water, of your body. So if you went under, totally underwater, the bathtub would go up a certain volume, more than when you started. The difference would be the volume of you. So what we can do is we can take a container of water. Let's say it was at 50 milliliters, and we're going to dump a chunk of fool's gold or gold in there. What's going to happen is the water is going to go up. Just like when you sat in the tub. The amount it goes up, say it went up to 70. That means it went up 20 milliliters without anything in it. So the volume of this green object is 20 milliliters. Because it went up from 50 to 70. That means the object displaced 20 milliliters of water. So let's go back to our miners now. So the miner comes in, plops this big yellow shiny object on the counter, and he goes, I would like to convert this into cash. First thing the guy does is weighs it and then puts it in water and sees what the difference in levels of the water goes up. So now we have mass, and we have volume, and the water displacement, and they just calculate that. So if the grams for volume is equal to 5-ish, because a fool's gold is not pure, neither is the gold. That's the fool's gold. If it's closer to I believe it was 19, wasn't it? Yeah, 19. It would be gold. And this is because of density difference. Now, and they look exactly the same. Fool's gold is a slightly different shade of yellow than real gold. But man, they're both metal, they're both shiny, and they both came from the same place. Yeah. Fool's gold per unit volume is much lighter than real gold. And almost worthless. Well, by today's standards, it would be not worthless, but almost worthless. So the miners would get nothing for the fool's gold, and they would get their normal amount for their gold. Now, the problem is frequently when you pan for gold, has anyone panned for gold?
I have a long time ago in elementary school.
Did you take a trip up to Sutter?
Yeah. Yeah.
Yeah, and when you do that, you don't get much, do you? It's mostly almost like big sand. And so now when they discovered gold, by the way, up at in the mountains, they had chunks of gold the size of your fist. And it was unreal. They would just pick it out of the stream in the beginning. It was unreal. Then that stuff was all picked over after a while, so they started getting more and more time consuming to get the gold, and end up being gold dust after a while. But basically, it's typically in small pieces. So what they do is they weigh all the small pieces, then dump it all into water, and see how much the water raised, how much the water was displaced, and that would give them a density. And if it was, I mean, these are pretty different numbers, 5 versus 19. So it's pretty easy to figure out which was gold and which was not gold. But it was density. It worked really well. And you don't need much of an apparatus to figure out the volume. You just need to have a calibrated volumetric device. And then your scale, of course, assuming it's accurate, you can find mass. So density is a very handy tidbit. Another little tidbit about density is if we look at temperature and density, when temperature goes up, density goes down. So whenever you give a temperature measurement, it is always at a given temperature, normally room temperature. So they always give you a room temperature normally, because it varies with temperature. Now, there are 5 things on the Earth which do not obey this relationship of density and temperature. One of them is water. When the temperature goes down, see, now this is for water does something strange. At 4 degrees Celsius, water changes density. Basically, it gets bigger. So when we cool water it gets smaller, 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 okay. More and more dense, same volume. And gets volume-wise, but the mass is the same, so the density goes up, 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 except at 4 degrees Celsius. Then water stops getting smaller and it gets bigger. So the density changes. Now the mass doesn't change. What happens is the volume changes. So at 4 degrees, water expands. And there are 5 or 7 substances, I guess, depending on how you look at it, in the world that do this. Now, that's what happens in the winter when your pipes freeze, is that once it gets below 4 degrees, which is still liquid water, when it turns to ice finally at 0, that water in that pipe has expanded and it will burst the pipe. When you get water in a crack in a rock, and that crack is exposed to freezing temperatures, that crack will get bigger because the water in there expands at 4 degrees. That's how a lot of erosion takes place in the mountains. If you go up, if you've ever done any backpacking in the granite area of the Sierras, you can see these large slabs of granite that have flaked off. And that's because the water gets inside these cracks in the granite. And granite is very, very hard, but it will take and actually crack that very hard granite. When this density changes, it is very, very strong. Whenever in Alaska and in cold countries, Canada, Montana, they'll have something called frost heaves in the road. And underneath, in certain parts, the water will gather there for whatever reason. And when the road freezes, the water will expand and heaves the road up because of this phenomenon here. And it's because of the density. Another interesting phenomenon is the fact that at 4 degrees, water changes its density relationship, is ice. Ice is less dense than water because of this phenomenon here. Oops. That's why ice floats. It's because its density is less than normal liquid water, above 4 degrees. Think about the world, what it would be like if ice did not float, where ice would be like normal liquids when they turn to solid, are more dense than the liquid from which they've come, and they sink to the bottom. Think about our world. 1, we wouldn't have any erosion from water, and 2, our fish would die every year because they wouldn't be insulated from the cold weather above. They'd have that ice to insulate them, and the water below would stay liquid. So density is another conversion factor. We can go from mass to volume, volume to mass, because it's a conversion factor. So that conversion factor can give us this relationship. Volume to mass, mass to volume. And a number of your worksheet problems have you go back and forth. Okay, that was what I wanted to cover today. Are there any questions about what we've covered today? I'm going to put some more worksheets up on modules. I'm going to put three more worksheets up, and they're on dimensional analysis, and they're just worksheets I copied off the net. And just to give you some more practice at this, because you really need practice at this. Now, the important thing is when we get to unit 5, we're going to be doing lots more of this. So the goal on unit 2, actually on unit 1, is to get comfortable with doing dimensional analysis, going back and forth between units, that sort of stuff. And I've given you on the worksheet, the official worksheet, lots of that practice. And please keep in mind, again, if you find any mistakes, please let me know. Because I was given the answers to this worksheet by one of the professors, but none of it was worked out for you. So what I did is I went through and painstakingly worked out all the problems with the setup, so you see exactly how they're worked. Now, sometimes it's a little cramped, and I apologize for that, but I wanted to make sure you have the setup down. So you'll see how I arrived at the answer. Okay. Excuse me. How are we doing? Wasn't that fun? Don't answer all at once now. Oh my gosh.